Greetings and salutations, everybody. Welcome to another Ocean Protect Stormwater Fundamentals series webinars. And a crowd favorite is back to fly the Quilty Engineering flag for 2025. None other than Sean Quilty. Welcome. Sean, how are you?
Hey, Brad. Welcome, guys. Thanks for taking the time to learn a little bit more about stormwater engineering.
Very cool. And look, Sean is a crowd favorite. He's a passionate educator in all things engineering and particularly stormwater. For those who don't know Sean, well, he is a director of Quilty Engineering Hub and an associate director at Pitch Black Group. And now he's all over TAFE Queensland as well. Creating the next generation of engineering superstars. And we're going to hear from Sean very quickly. And Sean's actually, this is the first of 3 sessions by Sean this year. So he's kicking off obviously today with Stormwater Channel Design, but then we've got him coming back next month on GIS Stormwater Engineering, and then with that, I guess wouldn't be stormwater without rainfall, Sean. So he's going to talk about rainfall. So exciting stuff. And look, if you haven't already registered, please jump on the Ocean Protect website there. And obviously, it's a lot easier if you subscribe to the newsletter as well, because we give these sessions a plug. Just a reminder in case you haven't registered already. Certainly a big turnout for our first one. I think we had about 670 registrations. I think last I looked, I think we were sitting about 600 or so for Sean's. That was a while ago. So big numbers. He knows how to drag a crowd, does Sean, and why not? And look, without further ado, I'm going to pass it on to Sean. And just a reminder, folks, if you are new to the webinar format, if you do have any questions you'd like to ask Sean, please put them in the Q&A. Generally speaking, first come, first dressed. If you just want to throw out a kudos and say Sean's a legend, feel free to put it in the chat. But if you've got a question, please put it in the Q&A. This will be recorded, and we'll have the recording on the I guess Ocean Protect website and YouTube channel probably within 24 hours, along with Sean's presentation slides. They will be under the oceanprotect.com.au/webinars page. And look, obviously, if you do want a CPD form, you should get one within a week if you've already ticked the box saying you want one. But if you don't receive one in a week or 2, just drop us a line at Ocean Protect. But without further ado, I'm going to hand you over to the tender care of Sean Quilty. Welcome, Sean.
Awesome.
And thank you, Sean, for giving up your time today. Much appreciated.
No, pleasure. Always a pleasure. Thanks, Brad. And just a reminder as well of the poll that's up there. If you want to jump in and just fill out that poll, it's always really useful to see some of the feedback. And then the more people that can fill that out, the better sort of understanding we have of the industry out there. And then we'll obviously share all of those results with you guys as well. So really worthwhile just flicking through a few of those multi-choice questions as well. All right. Thanks, Brad. I'm going to just share my screen and get set up. All right, just let me know. Anything's good there? Yep.
All good, Sean, from mine. So
all right. So today we're going to cover open channel design or open drain design. There's a lot of different terms. We'll get into that shortly. But essentially, this is just a bit of an introduction into how we can design an open channel and see how much stormwater runoff we can actually flow through different channels. All right. So there's a lot of different terms that are out there. We might call these things drains, channels, open drains, open channels. In America, they call them ditches. You might hear of table drains and all sorts of different versions, I suppose. We're all talking about the same thing, essentially. We're looking at a conduit or a shape that's going to convey water flow. And that can either be artificial, so it can be a human-made sort of product, like a concrete drain, or it can be natural. We could be trying to simplify what a creek might be flowing at a certain location. So when we look at channel design, or when we start talking about these channels or drains, we're looking at something that is characterized by a free surface. So the surface of the water is open to the atmosphere. And that's very different to, say, our pipe design. If you go back to the Ocean Protect webinars from last year, we looked at pipe design. That's when it can start becoming pressurized. But channel design doesn't have that same sort of characteristic. And then the flow is driven by gravity. So gravity is what's actually going to force the flow through the channel. And with gravity, we also need a bit of a grade on our drains as well, but we'll talk about that in a bit more detail to come. So when it comes to designing and analysing our open drains, there's what we're going to see today is, I guess, a very simplistic view of a realistic sort of problem. So we try to simplify a lot of the engineering sort of things that are actually happening. So there's an emphasis on smaller natural streams, creeks, and constructed channels. So if you're looking at trying to see how much flow is running through Brisbane River, for example, you wouldn't use what we see today, and that being Manning's equation. That's a bit too simplistic of such a massive river system. So this is more very small systems, usually what you'd see in when you're looking at road design, when you're looking at rural or urban drainage around subdivisions. That's the sort of scale that we're talking about when we look at these drains. So it doesn't include large systems. Please don't go trying to design a full river system based on Manning's equation. That's not the right tool for it. When you do get those sort of situations, that's where you need to get some more specialized expertise in hydraulics and hydrology and river engineering as well. So this is more the simple stuff that we're going to look at today. So as I said before, heaps of different types of open channels. I'm just going to call out just a few specific ones that we use within Australia. So the terminology, when people start dropping these terms, you can kind of see what they're talking about. But essentially, all of it's doing the same thing. It's an open shape that conveys water runoff. So we've got table drains. So table drains are located on the outer edge of our roads. Typically, that would be a rural road setting. No curb and channel. The water just runs off the pavement and drops into one of these table drains. So the purpose of this, we want to collect and then convey our runoff from our pavement, from our shoulders, and then any batters. So typically, your table drain will be located when you're in cut. So you'll usually have an upstream batter that would actually flow or discharge water into that table drain as well. So that's the purpose of a table drain, if you hear that term. The next one is a diversion drain. And so this typically is where we want to redirect or divert, as the name suggests. We want to divert that water that's collected, say, from our table drains to a designated outlet, or it might be to divert that into a much larger drainage system. So in this example here, we've got a highway and we have our table drains that'll be on the side of the road. And then we would have these offshoots or diversion drains. So once the table drain collects too much water and that drain hits capacity, we can then divert that water off to the side to go somewhere else. And so then downstream, you'd have a nice new table drain that would start collecting a new catchment. Usually we'll space these out to make sure that these table drains divert or discharge water at suitable spacings. But that's typically what we're looking at. Another note as well, and I do point this out because when we start looking at modeling these systems and we start working with a lot of the civil designers out there, when you have a table drain and then you want to divert it into a diversion drain, or you want to stop the water and push it through a culvert, please make sure you've got table drain blocks, essentially a bund at the bottom of that table drain. A lot of the time I've seen models where you would have a table drain that just runs right through, and on a plan it says the water's going to go somewhere else. But if you don't have a physical bund to push that water, the water's going to just keep running straight through. So just keep that in mind in the design space. And then we have side drains. So in this busy little diagram that I've got here, I'll give you a second for your eyes to adjust, but essentially we've got a road on the bottom sort of left to right picture. And then we would have table drains that would collect water off of the road and off of the adjacent batters if it's in cut. Those table drains will become overwhelmed or would reach capacity. And then we would divert those using a diversion drain. And then those diversion drains, it might just stop and sort of spread the flows as a level spreader, or it might drop into a more dedicated, larger drainage system. And that's what we'd refer to as a side drain. So it's off to the side of the road, for example, and it's dedicated for conveying and picking up those flows. So that's how you can kind of see we've got table drains, diversion drains, and side drains. But really, when it comes to design, it's designed all the same way. And we're talking about the exact same thing. They're just slightly different shapes, maybe different sizes and different flow rates. We also have catch drains. So as the name suggests, this is to catch the water, or sometimes they're called cut-off drains. So it's to cut off any of the water that's heading somewhere that we don't want it to go. So this will intercept the surface water. Typically, you'll see these at the top of cut batters. So in this diagram here, we've got a road that was just sort of recently constructed. We've got a table drain that's shown with all that disturbed earth, if you like. That's the table drain there. But then we've got this upstream portion where all that vegetation, that's a natural catchment, it's higher than the road. And all of that water will basically come down off of that catchment and head straight towards our road, or it would head straight into our table drain. Now, the problem with this is maybe we don't want all that water to drop into our table drain. Maybe during construction, we want to try to manage and control that water a bit better as well. Otherwise, you're going to have this massive sort of inflow of stormwater runoff. So this is where cut-off drains or catch drains are really useful. So what you could do is you could form one of these open drains on the upstream side. So just at the sort of the top of that cut batter. Construct those catch drains, and then that will catch any of that upstream catchment. And then you can direct it and convey that flow where it might be a little bit more suitable. So usually this is really good for preventing erosion on those batters as well. So you can kind of see that cut batter in the road and it's all grassed out. Once the grass has striked, it's a bit more stable. But during construction, that's going to be a bare earth surface. And you don't want even a small stormwater event coming through and all that water rushing down your earth cut batter, because it will form little rills and cause erosion, and it's a real pain to fix up. So typically with these catch drains or cut-off drains, you might see details where they're very, very small. It's only a few 100 mil deep, especially in erosion and sediment control. We use this quite often. But you could also have, obviously, size to whatever catchment you've actually got. But usually cut-off drains are sort of kept at that smaller sort of stage with that, with the term cut-off or catch drains. I have put a note there as well for erodible soils, and that's probably a whole other discussion. But if you do have highly dispersive soils that are subject to erosion quite easily, then you generally don't want to put in or carve in this sort of catch drains, because you're basically disturbing that soil and it's just going to erode through your catch drain as well. So you can't use them everywhere. You've got to sort of think about where you use those. We then have median drains. As the name suggests, these are used in the median of a roadway. So median drains, in this example, we've got a highway, we've got sort of a, northbound, southbound lanes, and then we've got this space in the middle. Now, when you get to quite large roads, quite wide roads, whether they're arterials or highways, you end up having, 3, 4, 5 lanes plus shoulders. You get quite a large catchment area where it's just the road picking up the stormwater. And so we've got to control that water runoff. And usually where you have these really wide roads, they're also of a really high importance. Because they're an arterial road or a highway, you can't afford these roads to become flooded in frequent events. So they can't be flooded every few years. You want to make sure they're dry as much as possible. So this is where we go away from having, say, curb and channel, and we're trying to keep the water next to the road. We actually want that water to sheet off of the road and just go away from the road itself. So we put in these medians, which is basically an open channel or an open drain in between, and that will allow all of that road runoff to actually drop into these median drains. Then we can safely convey all of that water somewhere downstream and control and mitigate that flow. So they're median drains. Again, exactly the same as all the others, just a slightly different environment that you would use them. We then have inlet and outlet drains. So if you think about a culvert and you've got some pipes, some head walls, when that discharges, if your culverts are lower than the surrounding surface, then that culvert's sort of in cut, you're excavating down. And so you want to make sure that that culvert can daylight. And what that means is the invert level of your pipes can continue to run at a minimum grade until it breaks out and hits the existing or the natural surface. And so that is where, instead of extending your pipes all the way out until it breaks out of the side of the hill, you would actually just open up a drain and have that open drain or an outlet drain and carve that out until you actually meet existing ground conditions, and then it daylights. It sort of pokes out of the hill, if you like. So that's another name for them, inlet or outlet drains, obviously if it's upstream or downstream. Batter drains is another one. And so this is where you're trying to convey water down a batter. And so typically they end up being very, very steep. And so you have very, very fast flows. And we'll probably touch on that a little bit later and the problems around that. But these batter drains, or sometimes they're called slope drains, or they might even be called batter chutes because they kind of act like a chute because the water just drops so quickly through them. But in this picture here, we've got an open drain or a cutoff drain, if you like, that's sort of on the top of the batter. We can't see it, it's just behind. And then that will convey the water down to this batter drain. So at the upstream end of that batter drain, there'll be a bit of a bund, bit of a pond, if you like, that's sort of sitting there. The water will hit the bund and then drop into this batter chute or batter drain. So it flies down. I think we might have enough time to touch on channel linings, but generally with these batter drains, you want them to be a hard line surface because it's going to be really fast. You're going to have a lot of erosion issues if it's not a concrete sort of line chute. So that's a batter drain, super steep and usually a concrete material that's used. Bench drains. So this is where we start getting into pretty deep excavations. So you might be looking at a pretty serious sort of a road, like a big arterial road or a highway, and you're in a lot of cuts, and all of a sudden your cut batters are 9, 10, 12 meters high, like a massive amount of excavation. And so the problem with that is you would have your cut batter, it would be so large that any water that comes down, it's going so fast, and because it's so long, you get a very high potential for erosion to happen, and you have these little rills that will sort of carve out of those batters. So we try to manage how much water is actually flowing down that batter. The other problem is if you get a massive amount of water that's flowing down a massive high sort of batter, you're going to have a huge issue right down the bottom near your road, where you're just basically getting this curtain, almost a waterfall effect down to your road. So we can divert some of that water by having these bench drains. So in that cut batter, instead of having one continuous cut batter, we can actually cut in a bench to form a bit of a drainage channel. And there's other uses why we would do this for the benches from a maintenance perspective and a safety perspective, rockfall. There's a few good reasons why we would do that. But one of the things would also be to have these bench drains to just control and convey that water as we need to. The list keeps going. There's a lot of different types of drains. You're probably seeing these and going, my God, I thought there was just a drain. It was just one type. But again, remember, they're all the same thing. They're doing the same purpose. They're conveying stormwater runoff, and it's an open sort of a shape. It's just the terms that are slightly different depending on where you would find these drains. So this is what we would call a contour drain, also called contour banks. So if they don't actually carve out a channel necessarily, sometimes they'll just put a bund and that'll be a contour bank. And this is to divert water along a gently sloped path towards stabilized areas. So in this case, we've got a really large sort of hill, big catchment. And if we didn't want that stormwater to rush all the way down the hill and then just hit the bottom of the hill, we could control some of that water by adding these contour drains or contour banks. So in this case, the white lines, if you like, that'd be the contour drains that you would carve out. So you'd carve a little bit of a channel and you'd throw that cut spoil next to it to create a bit of a bund. So you're kind of creating two things at once. And then those contour drains would have a very slight grade. So they're not very steep at all. And that's why we call them contour drains, because they follow the contour of that topography there. They end up almost looking like the contour lines that you would see on a topographical map, in fact. So this will slow that runoff to prevent that erosion. And then we would allow those contour drains to then finish at a suitable location and then just make sure that the flows that are rushing through or off of those contour drains are at an acceptable velocity, a very low velocity, to avoid any sort of erosion and any damage there. Swales, so I'm sure everyone's heard of swales, the terminology swale. Essentially, they're just an open drain, but they typically will use vegetation to help reduce those flow velocities and also promote sedimentation. So it'll trap some of that suspended solids as it's rushing through that drain. So sometimes we would have surface filtration, so it'll just go through the grass. And then, as a lot of you will be aware, using Ocean Protect philosophies, if you like, looking at stormwater quality, that's where we can turn these swales into, let's say, bio-retention type devices, where we can actually have media underneath to allow that stormwater to actually soak through and start to filter through certain media as well. So that's swales. Essentially, it's just an open drain, but you're using vegetation as a bit of an engineering solution there. So just a few of the terms there. So hopefully on your next project, if anyone drops some of those terms and talks about a table drain or a swale or some contour banks to control, you might have a little bit of an understanding of what exactly they're talking about. So when it comes back to the actual technical stuff, which we're going to cover today, we'll do a quick example at the end with some equations. There's a couple things that we've got to consider. The two main headings, if you like, we need to look at the hydrological analysis, so what's falling from the sky, and then we need to look at the hydraulic analysis, so how that water's behaving once it hits the ground. So from a hydrological analysis, this is where we need to determine our catchment, our rainfall, and then how that rainfall would then convert into excess stormwater runoff. So if you cast your mind back to last year's Ocean Protect webinar series, we had a rational method webinar, and we talked about this in a bit of detail. So if you are interested, jump online, jump on Ocean Protect's website and look at their past webinars to sort of check that out. But essentially, you'll determine how much rain is falling from the sky and then running down your catchment. So then you can start to look at, once it's on the ground, how do we control that in a channel design form? Sometimes you might also need to accommodate groundwater as well. So that's not when it's raining, but just water that's seeping through the ground that might actually end up seeping out of the, say, cut faces into your table drain as well. So sometimes you'll need to incorporate that. So we then have the hydraulic analysis. So once it's on the ground and that water is rushing down, and then we put an open drain or a channel, then we can start to understand and simulate how that water is going to flow. And that's our hydraulic analysis. So there's a few things that we need to consider. So we look at the channel shape. So we look at our side batters, our slope, our grade of our channel, the width, the depth, and another really important feature is the surface. So what is the surface treatment or the lining of this channel? Is it going to be just bare earth? Is it rock lined? Is it concrete? Is it grass? Is it vegetation? Because that will have a very big impact on the design of that channel as well. All right, so it's all pretty sort of high level at the moment. I think we've got a pretty good grasp of what we're looking at. Now we're going to jump into a bit of the fundamentals. So this is where you really start, grab your strong coffee and really focus in, because these are the nitty-gritty details that you need before you get into that channel design. So some of the fundamentals when it comes to open channel flow that we're looking at, we need to understand the velocity distribution first. And so this is just a bit of theory, and then we're going to simplify it for the equations that we use. But essentially, if you've got an open channel and you've got water that's running through, the velocity is not going to be the same the whole way through the channel. And in fact, I've got some contours, I suppose, or iso velocity contours there. And essentially, when the water's running through the channel, when the water's hitting a surface, it's going to have friction. And so that water velocity is going to be lower. So on the sides and the bottom of that channel, that velocity is going to be the lowest. Think of that contour line as maybe a meter a second. The next contour line inside of that channel, it might be 1.5 meters a second. And the reason why is as you get away from that surface, the water only has itself to sort of have friction against, and you're also going to have a bit of a momentum effect as well. Until eventually you go into that channel, and then right at the center where it's furthest from the channel lining, that's going to have the highest velocity. So this becomes really annoying when we come to channel design, because then we're left thinking, well, what velocity do we actually pick? And so this is where we'll see shortly that we'll actually adopt an average or a normal velocity. And it's sort of in between the highest and the lowest. Then we have to understand these two different types of flow. So we can have steady flow or unsteady flow. And then we're going to use one of those when it comes to channel design using Manning's equation and a couple other things that we'll look at today. So steady flow is when the flow rate and the velocity do not change over time at a given point. So if you drew a cross section through your channel and you're trying to work out how much water is rushing through at that particular point of the channel, we assume that it's going to be steady flow. So as an example of steady versus unsteady, steady flow would be if we had, say we had a bucket and we had a small pipe or a hose out of that bucket, and we turned the tap on and we turned it on so it sort of settled itself and there was a constant level in your bucket. So the inflow was making sure that that level didn't fluctuate. And if that was staying at a constant level, then the water coming out of your hose would be a constant flow rate, and that would be at a constant velocity. So at any point in time, as long as that water level didn't change and the inflow didn't change, you're going to have steady flow. The flow doesn't change. The flow rate and the velocity are the same. If you had unsteady flow, this is when the flow rate and the velocity does change over time. So as an example is, if I turned off that tap, then all of a sudden my water level in the bucket will start to drop. And again, if we cast our mind back to the, the pipe design webinar that we did, as that water drops, all of a sudden you're getting less and less pressure or hydrostatic head behind that hose. So your flow rate is going to drop and your velocity is going to drop. That's an example of unsteady flow. So they're the two types of flow that you could have. We then can break that down even more and look at whether it's uniform flow or non-uniform or varied flow. So uniform flow means the depth stays the same, constant along that whole channel. And for this to actually happen, you need to make sure your cross-section is consistent, the slope's the same, the roughness is the same, and the water has an opportunity to kind of settle itself to get into that uniform flow. Non-uniform flow is when that depth might change. So you might have, maybe your channel comes down, it goes around a bend. That would be non-uniform flow. The levels will change slightly. Or if you had a bund or a culvert at the end of your channel, those flow depths are going to change and fluctuate. So that's an example of non-uniform flow. And then we also have laminar and turbulent flow. So laminar flow is when the water moves in smooth parallel paths. So if you could see the little particles flowing through, at laminar flow, they're all in the same position in your cross section. Turbulent flow is when water actions. So in more real world examples, you'll see whitewater conditions where that might happen. So we've got a few things that we've got to simplify. So when we use Manning's equation, which we'll see shortly, we've got to make a few assumptions. So one of the, or a few of the assumptions that we have to make first, we assume that we're looking at steady flow. So the flow rate remains constant over time at a given point. So when we're doing cutting a section through our channel and we're working out how much water is flowing through there, we've got to assume that it's steady flow. And when we make that assumption, it just allows us to simplify a lot of those calculations. We assume that it's uniform flow, which means that flow depth remains constant across those cross sections. So if it's one section of a drain that you're looking at, maybe it's a drainage reserve in between, a few lots in a subdivision. Through that drainage reserve, as long as the slope doesn't change, we're assuming that flow depth is going to remain constant. Because we're assuming steady flow as well, we can also assume uniform flow. And then, as I mentioned before, with the velocity, that's going to change all the way through that channel shape. It's going to be a lower velocity at the surface, the interface of the water in the ground, but a really high velocity in the middle of the channel itself. So we assume that this velocity is averaged across the cross section. And then finally, we assume the flow is laminar. So there's a lot of assumptions that we've got to make. And when you think about it in a channel sort of design, sometimes that's not really going to be true in the real world. Your flow will probably be turbulent in a lot of areas. Your flow depth will change as it sort of meanders through your sections. The velocity is not going to be just perfectly the average. It'll be slightly different at the interface and so on. So they're just assumptions that we make to simplify our calcs. Now, if any of these assumptions are invalid, if any of these are not true in your particular case, then you really should do a more detailed hydraulics analysis. So that's where you might do flood modeling or even a 1D analysis using HECRAS, for example, to kind of see how that flow is going to change over the length of your channel. But we're going to keep to those assumptions for the calculation that we'll look at now. So when we're using Manning's equation, which we'll show shortly, we assume that the flow that we're analyzing is operating under normal depth and normal velocity. So you'll hear those terms, normal depth and normal velocity, when you start looking into the calcs. Normal depth is the flow depth in a channel under normal conditions, and that's determined using Manning's equation. Similar, normal velocity is the velocity in a channel under normal conditions as well. So it basically means that the channel's allowed to settle, if you like, and then that flow is allowed to operate as sort of uniform flow, and there's no real disturbance, or there's nothing that's really changing those flow conditions. So it's a pretty big assumption, but if you have a reasonably uniform channel and it's a decent length and nothing's changing every 1 meter, then you could probably take those assumptions and that'll be okay. And now we are going to use Manning's equation, but with that comes this Manning's roughness coefficient, or a lowercase n is what you'll see. So the Manning's roughness coefficient is essentially telling us how rough the surface is in our channel. So if you had a rough surface, you're going to have a large n value. A smooth surface will have a small n value. So there's a few different sort of topics there. I won't go into a great detail just because I'm wary of time here. But natural channels, artificial channels, grass channels, rockline channels, as soon as you change the surface finish, and not just the material, rock or concrete, but also, with rockline channels, you're going to have different sizing of rock. With grass channels, you're going to have different lengths of grass, different species. When any of that changes, we should really look at the Manning's roughness coefficient to make sure we're adopting the most suitable n value. All right, here it is in all its glory, Manning's equation. So when we look at this, Manning's equation will calculate the velocity. And when I say velocity, I mean the average or the normal velocity in our channel. So it's equal to 1 divided by Manning's roughness coefficient, or that lowercase n, times our hydraulic radius to the power of 2 on 3, times our slope of our channel to the power of 1 on 2. Firstly, the hydraulic radius. People will be like, well, what is that? We haven't really mentioned that yet. So the hydraulic radius is essentially looking at the cross-sectional area of your flow. So it's not the full channel, it's what the flow area is, divided by the wetted perimeter. So the wetted perimeter is, if you had your cross-sectional shape, it's the perimeter or the length of your surface or your channel lining that will be wet. So it's again based on that flow area. So once you find that, the area divided by the wetted perimeter, that will give you the hydraulic radius to plug into your Manning's equation. The slope, please keep in mind that's a decimal, meters per meters. Don't use percentage. Sometimes, depending on the values, you can get away with it and get an answer that seems correct. And then other times it'll throw it right out. So just keep an eye on those units. So technically with Manning's equation, the slope that we look at is the slope of the energy line. And that gets in a little bit more detail with regards to hydraulic grade lines and that sort of thing. But with the channel design that we use, we can assume that this energy line is equal to the slope of our channel bed. So really, if your channel is at 1%, then your slope will be 0.01. And then Manning's roughness coefficient that we mentioned before. Now, I have put a note here because this is stated in a lot of literature. If you start looking at different guidelines, they might say Manning's is fine, or different council plan scheme policies. But technically, Manning's equation can be unsuitable for irregular channel shapes. So if you're starting to look at a natural stream and it's sort of, you know, all over the place, different sort of shapes, and the bed's different and the batters have got bumps all through it, Manning's may not be the right solution for that, and some literature will tell you that it's not suitable. So just check your local council guidelines or your local standards that you're using. Okay, so Manning's equation will work out the velocity. We still need to find the flow rate. So we've got the velocity, we know it's flowing at 1.5 meters a second, but what's that liters per second or cubic meters per second? So that's where we use a continuity equation. So our flow rate is equal to our velocity times our cross-sectional area of the flow. So using that, we can then very quickly calculate our flow rate. The continuity equation, especially in channel design, we're assuming that it's steady flow. The flow is not changing throughout our typical section. So that means your flow at one point is equal to your flow at your second point. And that's where the continuity equation comes from. All right, so we'll crunch some numbers and then we should have a bit of time at the end for questions as well. So in this example, we're going to determine our flow rate and our velocity for a channel that's flowing full. So in this example, you might have a channel, and usually with channel design, it's a bit of a trial and error. You'll think of something, you'll crunch the numbers, and then maybe the channel's too small. Then you go back and redesign the channel. So in this case, we've got 1 in 4 batters. We have a 2.5 meter base width, and it's going to be 0.5 meter deep, and the slope's at 1%. And we're assuming this is a grass channel. So we're going to use a Manning's value of 0.035, which is pretty typical for grass. Again, we're assuming that the flow is full. So if we look at the whole cross-sectional area of the channel, that will also be our flow area. And that's what we need in the Manning's calculations. So we'll use Manning's equation. The velocity equals 1 on n, R2 on 3, S1 on 2. And then we can apply the continuity equation to get our flow rate. But first, we need to calculate the hydraulic radius. So that's our flow area divided by our wetted perimeter. So this is now getting into some pretty basic sort of maths. And so if we look at our flow area or that cross-sectional shape of our channel, there's a few different ways, or 2 different ways that I've shown here that you can do that. We can split it up into 2 triangles and a rectangle, work out the area, or you can use your trapezoidal formula where you have your base width and your top width and your height or your depth in this case. I won't go into great detail here, just wary of time, but it is there if you want to really crunch the numbers. Now, when it comes to the wetted perimeter, we want to work out what that sort of slope or that batter length is, plus our base width. So that's where you'll need to use Pythagoras. And a lot of you are probably scratching your head going, oh my God, this is now what, year 10 maths? We're going to have to pull it out. But just a reminder, so with Pythagoras, if we want the hypotenuse, we can use the equation a squared plus b squared is c squared. And we know it's a 1 in 4 batter. So we can sort of crunch those numbers. But again, I won't go through those in great detail. Essentially what we're doing is we're calculating the cross-sectional area. And then on the next page, we'll see the wetted perimeter. So in this case, I've just worked out the cross-sectional area using the trapezoidal equation. So we've got 2.25 square meters of flow area. Again, we're assuming that this channel is flowing absolutely full. So then we look at the wetted perimeter, and using the hypotenuse calculation, we can work out the length on both our batters plus our base width, and we get 6.623 meters. So now we have our area, and now we have our perimeter, our wetted perimeter. So we can calculate our hydraulic radius, R equals A on P. So we've got a hydraulic radius of 0.34 meters. Now we have all the information we need to plug it into the Manning's equation. So our velocity is equal to 1 on 0.035, our Manning's roughness coefficient, times our hydraulic radius to the power of 2 on 3, times our slope, which was 1%, but we put that in a decimal to get the units right, to the power of 1 on 2. We crunch those numbers, and then we get a velocity of 1.391 meters per second. So if this channel flowing completely full, and it was at a 1% grade, and it was grass, that flow you'd actually see flowing at 1.391 meters a second. Drop your stick or your leaves for a little boat race, and you'd see that travel 1.391 meters every second. Okay, that's that flow rate that we're looking at. So finally, we can calculate the flow rate, not just the velocity, using Q equals VA. We already know our cross-sectional area of our flow. That's 2.25 square meters. Multiply that by our velocity, and then we've got 3.13 cubic meters per second. And if anyone sort of remembers from some of our past webinars or courses, 1 cubic meter is equal to 1,000 liters. So that 3.13 cumex, or cubic meters per second, we can also call that 3,130 liters per second. Again, that's if that channel is flowing absolutely full. So that's how you can calculate, based on just the geometry of a drain that you might be looking at, you can calculate the velocity and then the flow rate. All right, so I'm just keeping an eye on time. So I think we're pretty good. We should have heaps of time for questions. But if there's anything that sounds familiar and maybe you've heard in the industry, so if you're looking at channel lining solutions, where you would use rock, grass, vegetation, geotextiles, concrete. If you need to start looking at hydraulic jumps and you're looking at subcritical, supercritical flows, if you don't understand stage discharge curves or rating curves, if you want to understand tailwater conditions, or even just get a general idea of design criteria, reach out. We do have workshops, and we can have all your answers, all your questions answered. We can run through hand calculations. We work through real world examples. And best of all, when we have these workshops, we problem solve within a group. So a lot of discussion and a lot of different perspectives, which is always really, really interesting and really, really beneficial. So anything that you're not really sure about, please get in touch and we can certainly help you out. So I'll just point out as well, so for workshops, we've done a couple of these workshops now. Essentially it just saves managers a heap of time. They can upskill their team. They don't have to be there. It increases staff engagement. You can achieve all your PD goals by joining these. You can fast track your career. Heaps of benefits there. But if you're just an individual, a student maybe, and you don't have a team or you don't have an employer to book one of these workshops, there's also an online course that you can enroll in as well. And for $49, you've got hours of content. You keep that course forever, lifetime ownership. And there's even a design spreadsheet to help crunch those numbers in your day-to-day sort of role as well. All right, I think I'll hand it over to Brad, and then if we've got any questions, we can sort of chat about channel design for the next 15 minutes.
I talk my love language, Sean. Sounds great. And thanks again, Sean, for an amazing presentation. The questions are coming in thick and fast. Like I said, generally, if you've got it's first in, first dressed. And please, if you do have a question, please put it in the Q&A instead of the chat. Makes jobs a lot easier. I think first in was Alex. Alex, and I'll just get the surname, Alex DeAndrade, I believe. Apologies, I mispronounced that. From Northrop in Brisbane. Alex asked the question, what is the process for applying this method to a varying surface channel, i.e. like a concrete spoon, and then the remainder is turf?
So if I get the question right, and hi to Alex as well, is a mate of mine. We've worked together and we cross paths in a lot of different functions as well. If you're talking about the one section and it changes, so you've got concrete at the bottom and maybe grass on the sides, that's where we would start to look at what we call a composite section. And we basically start cutting that drain section into pieces. And then we would look at individual Manning's calcs for, say, the batter with your grass, different Manning's value, different wetted perimeter, different area. And then you have the concrete, and then you have the grass on the other side. And you basically just add them up. It's a summation of those different sort of slices, if you like. There's two different methods. I won't go into great detail now, but there is, when you're looking at composite methods, you can calculate a composite Manning's roughness value and use the whole area. Or you can do this sort of slice technique where you cut them into different sections. I've used both in the past, and typically I'll just pick the worst case, because when we're doing these sort of analyses, we're really simplifying a lot of stuff. And so if we're simplifying it, there's a bit of risk there in case it's oversimplified. So if you've got a couple different options to do, I would always suggest just crunching the numbers for both different techniques and just seeing which one's worst and go with that to be conservative.
Cool. Thank you, Sean. Next question was Jacob Beats, all the way from the city of Vincent in Western Australia, already winning for the furthest question away. Look at the wonders of modern technology, Sean. Jacob asks, what would your best recommendation be to approach velocity calcs when encountering energy dissipators within your channel? Or would it just be a case of doing the hard yards and working out the wetted perimeter?
Okay. Shout out to Jacob. So he's a past TAFE student, and again, we've worked together a few times. So yeah, g'day Jacob. Hope you are nice and settled over there in WA now. All right, energy dissipators. This one's interesting because there are some guidelines. If you some people might have heard of the HEC guidelines, which is HEC. There's, I think, don't quote me, but I think it's HEC 15, HEC-15. If you Google that, that's a standard that they use in the US for their highway design. And I'm pretty sure there's a chapter in there or a big section in there on energy dissipators. If you wanted to do it properly, there are some equations and there's some, they're actually very good examples of different configurations of energy dissipators. So basically, anyone that doesn't know what that is, if you had your channel and there's really high velocities that are going towards the end, you want to slow down that velocity before it hits the natural sort of ground. You could have an energy dissipator of just a rock pad, so just big dumped sort of rock pieces or fragments, and that'll slow the velocity. If it gets too high, and usually that threshold is about 5 meters a second, if it's over that, then you might need to put in an energy dissipator. And so that energy dissipator might be, maybe it's a concrete apron and you've got these big concrete blocks that are sort of cast into that apron. So there's, nothing's going to move it basically. Anyway, with those energy dissipators, there's some equations and some sort of best practices that's in there. So HEC 15, I'd definitely have a bit of a read through that. Otherwise, something that I think we haven't really realized yet is the power of CFD. So that's computational fluid dynamics. And that's where you see really awesome visualizations where the water comes through and you see it splashing and moving around, but it's all based on science and physics. And I think what the future looks like, in my opinion, in the next few years, I think we would just model the dissipators in Civil 3D or whatever software. And then we would plug it into a bit of software that would then run a flow rate through your channel. And then you'll just see it hit and smash and move around, and you'll be able to assess what the velocity is on the downstream end. So it's not quite used in industry that much. The software is usually pretty expensive to sort of get and run, and it takes a lot of computer processing power, but you'll get a very, in my opinion, I think a very accurate answer there. But until then, it'd go back to the calcs. And even before then, if you can't even crunch all the numbers, I would just look at more sort of, I guess, evidence based on what's done in reality. Maybe there's a dissipator that Main Roads has had there for 30 years and nothing's gone wrong. Just adopt their standard and you hopefully will get out of trouble. Good question though, yeah.
Well, they're all good questions. Thank you, Sean. Another one from Matthew Kirby, who's an engineer with Toowoomba Regional Council. Matthew asks, should freeboard be included in the calculations, or is this normally just a sensitivity exercise?
Very good question. Yes, freeboard should be included in pretty much all cases. So freeboard is, if you had your cross section and we looked at the water was flowing right to the very top. So there's no room for error there. And so if that water was rushing through, it's a Q100 design, for example, and in a 1% storm or a 100-year storm, it's not going to be calm. You're going to have massive amounts of wind and all sorts of things going on. And so that water won't be perfectly just at the top. There's a good chance you'll get wave, it'll sort of hit sections, it'll splash everywhere. So that freeboard is where you have a little bit of a buffer, or that channel is a little bit deeper, and you're expecting the flow to reach a certain level, and then you've got this space up above. So typically for freeboard, if you're looking at some values, you would use the maximum value of 300 millimeters, or the 20% of the channel design is usually a pretty standard approach, or you would look at the velocity head. So if you're not sure about velocity head, again, go back to Ocean Protect's previous webinars, and we talk a little bit about that. Essentially V squared on 2G. So there's a few different ways to sort of calculate the freeboard, but then when to use the freeboard, it comes down to risk. If I'm looking at water running through a spoon drain that's only like 40 mil deep and it's just taking water off of the car park, I wouldn't use freeboard. You don't need to incorporate freeboard there, because if it goes, outside of that drain, it's just going to hit your car park surface, no problem. If you were designing a diversion channel that's running through people's properties and it's getting water from one side of the neighborhood to the other, I would definitely include freeboard, because the risk is much higher. If it breaches your channel, then all of a sudden it's going to somebody's house. That's a very different story. You would definitely need freeboard. Again, go to your local council standards. Usually they'll have a clause in their planning scheme policy about freeboard, or they might refer you to maybe QDM for Queensland, or other sort of state-based guidelines as well. Yeah, good question.
Cool. Another one from Jude. They're all from all over Australia. We had Brisbane, Toowoomba, WA, and this one's from the city of Playford from Jude. Jude asks, what are the optimal design strategies for integrating structures like retention basins and culverts with infrastructure to effectively manage peak flow rates in stormwater systems, especially heavy rain events?
That's a big question. Sorry. So just repeat the start of that question again.
Yeah. What are the optimal design strategies for integrating structures like retention basins and culverts with infrastructure to effectively manage peak flow rates in stormwater systems?
Gotcha. Okay. So the design strategies. If I'm answering this correctly, and this might be, we could probably talk for half a day on this, but I think there's a couple of things to think about when it comes to stormwater management and a design strategy, if you like. As soon as I get any sort of concept design, I will always look at a quick, fast approximation of what's happening, and then try to gauge what the worst case is. So, for example, if you were looking at a subdivision, and they're going to have pits and pipes, and you're going to have roads that will essentially act as a channel, an open channel, and you've got to get the water from your catchment down to, say, a river or something where you're discharging to. One of my approaches is always ignore all the pits and pipes, forget that they're even there, and just look at overland flow. And if that 100-year storm came through, can you safely convey all that water through channels, whether it's roads or dedicated drainage reserves, and get out to the point of discharge? And then you can always, finesse it. I know I'm going to get a lot of knockback from that. And they'll say, oh, well, pits and pipes do stuff too. But at least you don't have to rely on your pit and pipe system. And usually when you have those major events, the pit and pipe systems will fail. There'll be a blockage somewhere, there'll be overcapacity, there'll be backwater effect, all sorts of stuff will happen. So that's one really good strategy. Don't rely on really small scale sort of infrastructure. Another, and I don't have the answer to this, but another approach is to incorporate climate change, which is a massive unknown. It's a massive dark cloud, pun intended, that just hangs over my head as an engineer. We don't really know how to manage climate change. We're getting estimations and forecasts of what that might look like with regards to rainfall. We know that our storms are going to be more intense. We can already see it happen just in the last 10 years. And we also are finding that our storms are going to be more front loaded. So you're going to have that peak early on in the storm rather than sort of a mid-loaded storm. So I would say that part of that strategy would also be accounting for what might happen with climate change. And that isn't just a specific value or a specific number or a table you look up, but it's actually a spectrum. It can be, well, if it's not as bad as what we think, you'll be down here. If it's really bad and worse than we think, and we've estimated, it'll be here. And so you've got this spectrum of what might happen, and then you would analyze the risk. Are we happy to accept the risk at the low end and then at the high end? So that's probably what I would incorporate as well. Just how does climate change affect your design? And that might mean if there's more intense rainfall and it ultimately ends up with just more stormwater flow, then you might need to design your channels now to convey your flows now. But then in 80 years' time, when people are still living there, those channels might have to be built up, maybe progressively increase, or maybe you need some planned, land resumption, knowing that your channels are going to be twice as big in 60 or 70 years.
Cool.
I'll leave it at there. But yeah, a lot of things that obviously you would sort of think about, but that's a real high level planning sort of question, which I love. Yeah, that's good.
The speaking questions, we're going to allow, there's 3 to go, and I think we'll have to cut it there because we are running out of time. But Justin Sweet from Griffith University and Nathan asks, can you create your own coefficients for Mannings?
Yes, you can create your own Mannings value. I'm trying to think of some examples. I think is it Strickler's equation? There's an equation for rocked channels, depending on the rock size and maybe even shape, the uniformity and a few things. You've got an equation that you'll actually get an N value, 0.063 or whatever it happens to be, based on the material that you're using. There's definitely one for rock line channels. You can create composite Mannings values. If you have a bit of rock and a bit of concrete and a bit of grass, you kind of almost like just mush up that section into a composite section and use this like theoretical Mannings value. So it's not as smooth as all the concrete sections, it's not as rough as all the grass sections, and you sort of find this midpoint somewhere. So yes, you can. Yep.
Cool. Question from Ian Malecchio. Apologies, I mispronounced that, I'm sure, from Colliers on the Sunshine Coast. Ian says, hi, Sean, brilliant presentation. Nothing wrong with a bit of kudos to start the question. He asks, are there restrictions on maximum depth within channels? Also, could you give a small description on freeboard? What it is set against? Is it measured against the top of the channel or adjacent building pad level? So which one do you want to start first? I guess.
The maximum depth. There may be some requirements where councils might put something in place, or some guidelines might put in place where you don't want a certain amount of depth. But the more common value or parameter that we use is the depth velocity product. And so that's where you take your depth and then you take your velocity and you multiply the two. And then there will be a threshold where we found that any more than that value becomes dangerous. So as an example, a DV of 0.6 square meters per second. So it's like this flow area that's flowing every second. That's a pretty sort of common one to use for safe channel design. And the reason why we use the DV values rather than just a maximum depth is you could have, say, over a meter high of water, but if it's traveling super, super slow and someone got stuck in there, they can kind of wade their way out and it's not that dangerous. Whereas you could have maybe half that depth, only half a meter deep, and you think, oh, well, that's safer. But if that velocity is screaming at, 4 meters a second or something, the pure momentum of that will actually knock you over. And so that's the philosophy behind depth velocity product. So that's probably one thing I'll check. The second part of that question was the freeboard. So I did touch on a little bit before, but where it's measured, sometimes depending on what the channel is, like if you're looking at like a creek system, which is a pretty big channel, and you had to divert a creek, or you had to maybe rehabilitate a section of a creek, the freeboard would be to the top of your bank, I guess. But really, freeboard is measured to the threshold of where you don't want the water to go, essentially. So if it's a creek and then you don't want it to spill out into like maybe open parklands or whatever for a particular storm frequency, then you'd measure it to the top of the bank before it breaches. If you've got properties, usually that freeboard is measured to the finished floor level. And so that's the kind of space, because if it broke higher than your depth of flow that you were expecting, but it spilled out onto the roads or parks or even the driveway, but it didn't hit your house, then you're still safe. And so the flow is operating within that freeboard area. So it's not an exact answer, I guess, but it's something that you could definitely check with local standards, council standards, QDM, TMR documents, and they might give a bit more guidance where they'll tell you exactly what freeboard to use and where that's measured to as well. But yeah, typically any sort of residential stuff, it'll be to the finished floor level.
Cool. And this is the last question from Yelena. Yelena Shrev from Stantec, and I actually was doing a lunch and learn with the Yelena and the cool cats of Stantec on the Gold Coast just a couple of weeks ago.
Nice.
Amazing, beautiful plant-based lunch. Sean, you should have been there. Yelena, I say that because
where was the invite?
I know, right? Yelena's a fellow vegan, so we always look after each other. But that's it. But Yelena asked a really good question, and she's been very patient. Yelena asks, what roughness value would you use for a freshly built grass channel just after construction phase, when the grass is still establishing and it's prone to erosion? And this is probably a related question that I had. Vegetation changes. You got sometimes vegetation will die back. Sometimes the vegetation can stand up to flows, but also sometimes fall over, like Lamandra. Roughness changes. So how do you design a channel that changes?
First, shout out to Lena, so an ex-TAFE student, and we work together a couple of different places as well. So yeah, glad to see you joined. It does change. What I would typically do in any of my channel designs, grass is a good example. If we're looking at a grass channel, there's going to be a couple of different phases. But if we look at the worst case, or the two ends of the spectrum, you would have it when council have just constructed, or maybe just maintained. Maybe they've gone in, they've just dug out a whole heap of sediments, a bunch of weeds, and they've basically stripped it right back. I would look at the condition of that channel there and see what would go wrong. And so in that case, it might be bare earth. So the grass hasn't actually struck yet. And if that's the case, then your Manning's value would be like 0.02 or 0.025 or something, like pretty smooth. And the problem with that is, if it's a smooth channel and you crunch the numbers with Manning's, you're going to have a very high velocity. So if you've got a high velocity, then you've got to look at what is the threshold between the velocity between the water and the surface. And if it's bare earth, it's very easy to erode. So your acceptable velocity, or your maximum allowable velocity, will be quite low. I'm just picking numbers out of my head, so don't quote me on the numbers, but you might be limited to, say, 1 meter a second. You can't have more than 1 meter a second. So with that channel design, your Manning's value becomes really smooth. All of a sudden, you've got a really high velocity, and you've got to keep that velocity down. So then you have to look at your channel and maybe make it wider. The depth drops, the velocity drops, and it's acceptable. So just after construction, it'll handle. During maintenance, and they strip that back, it'll handle those flows as well. So that's one example. Then when they don't maintain this channel, or you have, summer, you get a heap of rain, you get a heap of heat, and everything just explodes and grows like crazy. All of a sudden, the grass is like 250 mil high, weeds, there's sticks all caught in and everything else. I would also design the channel for that condition. So it's very simple. You just look at a different Manning's value. It's very rough. So that Manning's value might be 0.06 instead of 0.03 for a standard grass. So it's twice as rough, or maybe even more. Calculate using Manning's equation. Now, all of a sudden, the velocity is going to be a lot lower, and you think, oh, that's great, it's not going to erode. But the problem we have is when the velocity drops, the water starts rising up in depth. So you get a much deeper flow. So all of a sudden, that might break out of your bank, break out of your drain, and doesn't work. So they're the two sort of things I look at. What's the fastest, smoothest it'll ever be, and what's the thickest it'll be? The smoother surface means a high velocity, so erosion's an issue. The really high rough surface means depth's going to be an issue. And then if you design your channel for both those cases, then you know you're safe. And the final thing I'll say just on that, with regards to construction, you don't necessarily have to design for the construction phase. So you might design it for the grass to be fully established, but when they're constructing or when they're maintaining it, they might have to put in erosion and sediment control measures until that grass has taken. And they're notes and stuff that you can sort of put in engineering drawings and specs and everything else. But yeah, again, a great question, but I would crunch numbers. Don't be, I'm not saying Lena's not, because I've worked with her, I definitely know she's not, but don't be lazy. If it means that you've got to just crunch numbers twice for two different conditions, just do it. For the sake of an extra 10 minutes, you'll be able to sleep at night.
And dream about Manning's coefficients and roughnesses till the cows come home. Great prezzo, Sean. We've got a lot of great feedback from all sorts of individuals all across Australia and beyond. Really thoroughly enjoyed your presentation. Before you go, just a reminder, folks, if you just didn't catch enough of Sean's dulcet tones today, you can actually watch it all again on the recording that'll be made available on our website, that webinar's website, in the next day or two. CPD forms should be coming out very soon. If you don't receive it next week, just email that address. And if you're not already sick of Sean's dulcet tones, whether it be the recording or live, don't worry about it. You can actually tune in again to see more of this amazing engineering educator on the next month's webinar, Wednesday, 12th of March, GIS for Stormwater Engineering, and the 9th of April about rainfall. And if you haven't registered already, you can obviously just jump on that website there and be sure to check in. And obviously, we didn't get to everyone's questions. There's actually quite a few coming towards the end, and unfortunately, we do flush out of time. But if you do have any questions you'd like to ask Sean, please feel free to reach out to him. And feel free, Sean, if you'd like to share your contact details. Yeah, again, if you'd like to reach out for Sean, whether it be email or LinkedIn, whatever, there's his details there. If you want to tune in or register one of his courses, highly recommended. Again, thank you everyone for tuning in today. And again, big shout out to Sean for giving up his time and expertise to talk us all about channel design. So thanks, Sean.
Thanks, Brad. No, thanks for having me, and look forward to the next one.
Boom. See you guys. Enjoy the rest of your day.
Thanks, guys.